Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Continue with the method number 2. We've looked at method number 1, which is the calculation that I've always used, and method 2 is allowable under a special code case to use division 2. So but of course you can only really use this division unless your client wants you to, but it does give you an outing. Say for example you have issues with regards to you want a little bit more room in your calculations and existing design. This is a practical way out to get a little bit more room so that you don't have any issues with having to modify your equipment. So we're going to take a look at step 1. Assume the thickness T and the unsupported length L. In this particular example, you notice that L shows up with division 2, and that's important because it allows us to more accurately do the calculation. So we're going to refer to part 4.4.5 cylindrical shell. And we do some number jungling at the beginning to make sure everything is okay. So we're just reconfirming in our minds what the unsupported length is according to the definitions. If you recall in the earlier slides of this presentation, there was a definitions for what L is. And of course we're adjusting for the corrosion allowance in this particular example, and we're going to continue. So we do the math, and again, so this is pretty much dead on. Is figure 4.4.1 is the same. So in our case, we're looking at the one on the left side, which is shown right here, and we'll continue. So we're going to do our step 2 is predict the elastic buckling stress. FHE is the terminology, and I put everything onto a spreadsheet because it's very meaningful to that. And basically we calculate the outside diameter, which is a key variable in doing the math, and then we calculate the MX, okay, and then basically we use this for dimensional checks. And so is MX greater than this ratio? In this case it's true, so we would use this value. More to come in the next slide. So we're going to continue. If this is the case, the check 2 is also applicable, then we would use this equation instead. And in this case, when we do the number juggling, right in between these two values, so we need to do that one. Now there's one more step, check 3. And related to the geometry. And if our MX value is between these values, then we have to use this relationship. I didn't bother showing you the math, but in this case, we wouldn't be using it. We would be using the check number 2 answer for our to figure out what our allowable external pressure is. To show completeness of our work, there's actually a dimensional check number 4, a condition of this value, but we didn't need to continue. We got to step 2 or check number 2, and that's what we're using. But there is more for more conditions. So the next thing we want to do is we want to continue this, and we want to finalize our HE calculation. So recall that we have our recall that we have our value here. We calculated the elastic modulus and the thickness of our part and D. That's not a problem. And then of course we figured out in the previous preamble step the CH, what we did based upon the shape, the dimensions of the object. And then basically we calculate our elastic buckling strength to be, it's quite high. It's 4,500 PSI. And basically, there's the metric version right there. Now, if we continue this, there's step 3. There's actually quite a few steps here. And this is called a predicted buckling stress, FCI. Okay, and so we basically go through these steps. And I want to just mention that this is for 2017 and earlier version. In our particular presentation, we're using the PTB examples from the 2013. I'll add on at the end of the presentation what's shown, and actually they just recently published 2021 example guide, and there's some really interesting stuff of how to do that. But I'm going to focus on this one. This is the one I've always used, and so basically I have a ratio here, and we do this. There's 3 steps. So this is all conditions. So first thing I always do is set up the ratio of, that elastic buckling over Y, and you get a ratio. And then basically you can sort of plug that into here and then, get a conditional statement. So it says false. I can't use this equation to determine my predicted buckling stress. So I got to continue. So then I go to step 2. Is it between these 2 values, this ratio? Well, in this case, it's false. So then I can't use this equation or this equation to determine this. So then I got to continue down. And then finally, I have an answer of this ratio. So what you'll find is this is like a discontinuous series of numbers. And so in this case, we're true in this one. So this is the value we would use based upon FIC is equal to HE, which we determined in the previous step 2. So last step is we're gonna calculate, FS, right? It's our, design factor. Some standards are trying to get away from design factors and go using like allowable stresses. But anyways, this has not changed. The previous step 3 has changed after 2017, but this has remained the same as far as I know. And basically, FS is 2 if we've got buckling stress is considered to be elastic. And then they say, FS is equal to 1.667 if buckling stress, is FIC is equal to the yield stress at temperature. And then they say, well, you can use a linear variation between, these 2 if you want, which can be kind of tricky. So I'm thinking the linear variation is the FS. And for combination of loads such as earthquake loading or wind loading, then they're saying increase your FS by 1.2, so a factor. And there's more statements finding that, but it's largely shown in 4153 for combined loads. In our case, we're just looking at the external load, and we're ignoring the internal pressure issues and so on for this particular example, so that the example doesn't blow up in complexity, right? So we're going to continue here. So we calculate the predicted buckling stress FS. Okay, so we've got we did the math. We talked about all this, and we said, is this case true? And yeah, it is true. So we're going to use, this this factor here of 2. The other cases are shown here, and we mentioned in the earlier slides about the elastic and so on. So these are the other 3 conditions. So the way it's set up, it catches everything. So in this particular example, we're using 2.0. So we go ahead in our final step 5. We found our FS, we know our FIC, and then basically we do this, and we basically cut that in half, and then then we use FHA, we drop it into here, and then we calculate 48.9 or 0.337 megapascals. And we continue onwards. We have, if the allowable external pressure is less than the required external pressure, then we can either increase the thickness of the shell, kind of alluded to in the method 1 methodology, but you can also do something like you can reduce the unsupported length, right? And by the addition of stiffening rings, and then go back to step 2. Because in this particular example, you can take advantage of the reducing the unsupported length to get to your answer, which is typically tends to be the most economical. When we were working on pressure vessels or vacuum lines, we would tend to always use vacuum rings to get around that because it tends to be the lowest cost. And we just repeat this cycle until this allowable external pressure is greater than basically a required external pressure. So I'm going to deviate here a little bit. We're going to look at step 3, which is the predicted buckling stress. This is for 2019 or later. This got really complicated. I'm going to tell you that. So they calculate the elastic buckling factor ratio, AE, which is shown here. And basically, when I did the math, my ratio here was AE over this, and this is the ratio that we start with. And so we continue on with that, and we calculate the predicted buckling stress. So basically, just step 3 that changes. Once we get through step 3 with the 20s. Later than 2017 version, so you work in 2021, you're basically just changing one step, which is step 3. And the reason why they're doing this is, is because they want to get a more accurate calculation and catch more materials with that. So they want you to work to a curve. So we calculated this value. And then we continue on. So we calculate the predicted buckling stress with this or later. So we solve in the elastic buckling stress IC through the termination of the material's tangent modulus ET based on a strain curve model at the design temperature per procedure this. So basically it's an iterative process that you can see here, and there's a table of this, and then there's a methodology they give you an algorithm to write to iterate a better solution. And so basically the whole idea behind this a big step up increase in complexity is they really want the user to develop strain curves for the material of interest at the design temperature. So they really want you to sharpen your pencil. And so, and that's basically why they're doing it. So I'm going to show you roughly what these equations look like, because they're quite intense. You can see them here. So, we, instead of these simple ratios, now we've got this, and then we basically do have D1, which you put in there, and then in here, and in here, and M1s and some of these factors here are found in tables, but you're having to assume your true stress and iterate using that one for this equation. So there is a program to use. I haven't really got there myself because I was using the previous version for quite a long time. But if you would like me to study this in detail, just send me some emails and maybe we'll get to that. Make some conclusions here. So about the allowable external pressures. So when we did the division 1, we came up with 39 psi external pressure. And we have division 2, which is 48.9 external pressure. And basically then we did the other one, which is the big step up in complexity. I did that and I looked at it, the later version of PTB, and I found that they were basically the same values. And I think what's happening is with, because they're asking you to develop your own curves, is that if you have like alloy steels and something, I would expect there to be some more of a deviation between these values, but that's just speculation right now. Now, I want to have a note about the combined loading. So cylindrical cells subjected to external pressure and other loadings, I need to satisfy the requirements of 4.4.12. Have a look at this. In this example problem, the cylindrical shell is only subject to external pressure. So if you have internal pressure and external pressure, and then there's the cyclic loading effects, this can get pretty complicated pretty quickly. So I hope that you found this this presentation useful for you.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.